This video is going to look at the continuing of chapter 21, adding reactions based on their equilibrium constants, and then looking at neutralization reactions with buffers and titrations. So when we're adding reactions, our general rule is going to be that the K's are multiplied. So if we look at these two specific reactions, each giving a K1 and a K2, we can look at species that can be canceled out, right? So we can go ahead and add these two reactions, and we can see that the NO3s will cancel and the NO2s will cancel to give us our new balanced reaction, removing anything we see as a reactant and a product. If we are able to do this, looking at these two reactions, what the K for this reaction at the bottom, or K3 is going to be equal to K1 times K2. And we could continue to write our K3 expression with our products over reactants. And if we had any coefficients here, those would be exponents, just like any other equilibrium expression. Let's try to do that with numbers. So here I'm trying to figure out, given these two reactions, what do I need to do to manipulate them into giving my reaction of 2NO plus Br2 yields 2 NOBr. Well, I can start with the first one, and I know that my NO is going to need to be on a reactant, so it's going to need to be on the left side. And my second reaction is going to have the NOBr on the product side, so I'm going to have to switch that one. Just like we've done with other calculations like this, we can go ahead and add these reactions. I know my nitrogens are going to cancel. I know my oxygens are going to cancel. And that's going to give me my desired reaction. So, like we did with Hess's law, I know that since I used my K1 reaction as is, K1 is going to stay the same. Here I did the reverse of reaction number 2. So I'm going to actually have the inverse, or 1 over K2, to get my equilibrium for the reverse reaction. And then in this case, K3 is going to be K1 times 1 over K2. And so I can put my numbers in, and I'll get an equilibrium expression of 2 times 10 to the third. Now, on the other hand, what happens if we're asked to calculate Kc based off of two reactants coming together, right? So I'm saying here a neutralization reaction with a weak acid and a weak base. Well, I would go ahead and write that reaction. But when I'm looking through tables or an appendix in the textbook, I'm not going to have any values for an acid or a base that aren't reacting with water. And so any value I look up for a reaction, I'm not going to be able to find what HF does with anything other than water. So what I need to do is to use the information at my disposal. I'm going to start with writing my weak acid reaction with water. I know what the value of that is. I then will also start my reaction with my weak base with water. And if I look at these two reactions, I don't have the exact identical reaction to my reaction in black. So what extra species I have here are OH minus, H3O plus, and my 2 water molecules. So I can use the ionization of water to help me balance everything out so that I have only what's left in black, right? So my waters will cancel. My H3O pluses and my OH minuses will cancel. And so if I start to add all these reactions together, I will exactly match what my black reaction says. And if I think about now, how would I get an expression for it? I know what the first reaction is. It's going to be Ka. I know what the second reaction is going to be. It's going to be Kb. And I know that the third reaction is going to be Kw, or 1 over Kw, because we are going from OH minus to water. So I have an expression again where I can go ahead and create numerically what my K for this bottom black reaction is. Pause the video now and try to complete this on your own. Okay, so really it's just plug and chug from there and making sure your math operations are correct. But what I'll get out of those terms would be Ka times Kb divided by Kw. I can go ahead and put my terms in, and I will have a Kc of 1.6 times 10 to the fourth. The next topic is going to be looking at neutralization reactions, and we're going to make a general rule that when acids and bases neutralize, these reactions go to completion, except with very weak acid and weak base, or with very weak base and weak acid. And so I'm going to show you an example of why we can make this claim. Not something you will have to be able to reproduce, but it does bring back one of the topics we talked about in equilibrium, so I did want to show an example. Here we're saying assume reactions go to completion, so that should remind you of something we've talked about early in the semester. When we're talking about going to completion, right, we're saying initial prime is a way we can use these calculations. And so in the future, what we're going to be doing is if we have acids and bases together, we can just assume it will go to 100%. I'm going to go through an example that helps show why that works. So if I wanted to use the exact same reaction I had on the last exercise, what if I wanted to calculate all the different concentrations that I had for the species in a 0.1 molar HF and a 0.1 molar COO minus? Well, I can use the same reaction I wrote earlier. I could go ahead and set up my ice table involving my 4 species. And initially, the question's saying that I have 0.1 molar of my reactant acid and my reactant base. But if we're going to say that we can make a generalization here, meaning that we're going to assume completion, we can go ahead and say that if I have these conditions, what really is going to happen is all of them are going to turn to products. So my initial prime will allow me to use my concentrations of my product acid and base. If I have my concentrations of products now, I know that my change is going to be going towards the left, so I'll be increasing my species on the reactant side and decreasing my species on the product side. And if I use my approximation based off of my Kc value, 10 to the fourth, I will have an estimate of 0.1 molar for both products. So if I wanted to set up my equilibrium expression, right, we have this from our Kc, I could go ahead and put my numbers in, and we would solve this just like we would any other traditional Kc question. We could multiply over, divide, and take the square root to give me my new X concentration. And so if I look at this, what I'm seeing is that this number is really small, right? And so in our example for our Kc, we picked 1.6 times 10 to the fourth. And what we showed in lecture was that no matter what other types of weak acids and weak bases, this is the smallest equilibrium constant we're going to see as far as magnitude, a 10 to the fourth. So what that means, and I can go ahead and check to make sure my approximation works. I end up checking it and getting exactly 1.6 times 10 to the fourth. And so I can actually recalculate my concentrations, and we're seeing that not only is it not a significant amount, when we round this up to the correct number of significant figures, we actually would see this being almost identical. And we would still have some concentration of my reactants, but again, it's almost negligible. So this is an example where you wouldn't have to redo this one via an ice table, but I wanted to show you something we've done with equilibrium that also applies to why we're making this general rule with acids and bases. The next topic we're going to talk about is buffers. So buffers are really important because these are solutions that resist large pH changes when you start adding any acids or bases. And so in order to be a buffer, you need to have a weak acid and its conjugate base, or a weak base and its conjugate acid. This is going to involve using Le Chatelier's principle in mathematics, meaning so that when I start to have any added base, whether it be any type of hydroxide, it's going to start to neutralize the weak acid. And my weak bases are going to be neutralized by any added acid. And so what we're going to see is a shift in concentrations between these two species, depending on whether or not acid or base is added. In addition, we're going to be able to use a new equation for us that's basically derived from our traditional ice table equilibrium expression. Let's go through that derivation now. If I started with a simple acid reaction using a weak acid HA plus water going to its conjugate base plus hydronium, I would have this following Ka expression. If I wanted to keep going without putting numbers in, I could go ahead and cross multiply my Ka and my HA concentration, giving me my conjugate base and my hydronium ion concentration on the other side. And then I also could keep going one step further and say, let's rearrange this, and so that instead of trying to figure out what my Ka is, let's figure out what my hydronium concentration is. And this essentially is a simplified version of what we do when we look for our X value. The next thing we're going to do is let's go ahead and take the negative log of both sides. Why would we want to do this step? Well, taking the negative log of my hydronium concentration is going to give me my pH. And in addition, if I take the negative log of my Ka, that's going to be able to give me my pKa. So the only piece that's staying together is the log of my acid over the log of my base. And again, going from those two steps is our log rules, where we're splitting out the product of two compounds. The negative log of hydronium is equal to pH. The negative log of Ka is going to be equal to the pKa. And this form, while mathematically correct, we actually end up switching my terms in the log. The reason why for this is that sometimes this negative log value is going to be negative, and so that way you never have to get confused about subtracting a negative and what that does. Now you're always either going to be adding a positive number or adding a negative number, which is just going to be subtraction. So I'd say this version actually helps you just complete the math without getting messed up by any extra negative signs. So this would be your standard view of the equation, where we have our initial base concentration over my initial acid concentration. Before we get into our traditional buffers question, let's focus a little bit more on why buffers actually matter and why they're important. If we started with a 500 milliliter solution of pure water at 25 degrees, we know that the pH should be neutral at 7. Let's see how just 2 milliliters of an acid can actually change that 500 milliliters of pure water pH. So what I would do is, in order to figure out what the new pH is, I would then need to configure out how many moles of acid I've added, right? So I can use my milliliters and I can use my molarity to get how many moles of HBr I've added to my solution. Since this is a strong acid, this is going to be equal to my hydronium concentration. In order to go from moles to pH, we're going to need to go from moles to molarity. So the next thing to do would be to add my volume from my addition of 2 milliliters of acid and my original 500 milliliters of solution. From here, I now have how many moles of acid I have present. I have a volume. I can go ahead and get a total molarity of my hydronium concentration. Once I have my hydronium concentration, I can take the negative log of that. That would give me the pH. So just looking at adding 2 milliliters to a 500 milliliter solution, we've gone 5 pH units. And we're going to do a lot of these types of calculations. So let's do another one looking at just base. In this example, I also am adding 2 milliliters, but I'm adding it of KOH. I'm going to do this one the exact same way. I'm going to use my milliliters of my base as well as my molarity in order to figure out how many moles of hydroxide I've made. Since this is a strong base, I know that that's going to give me the same amount of moles of OH minus. I have the same problem before. We're doing stoichiometry in moles, but in order to go to pH, we're going to need to do that in molarity. So I have the same volume, 0.502 liters. I can take my moles of OH minus over my liters, and I picked all the same volumes and molarities, so we're actually going to see the same concentration. We have an extra step here this time because we're looking at hydroxide instead of hydronium. So if I take the negative log of that, I'm going to get the same number, but remember that that is POH, so I would still need to subtract from 14 to get my new pH. And so again, we're looking at shifting almost 5 units up in order to get a new pH, even though we've added only 2 milliliters. And so the point of this exercise is to show you that a tiny amount of acid or base can really affect pH of pure water. Let's look at how added acid or base affects the pH of a buffer. And so let's go ahead and set up some guidelines to how to solve these problems. The first part of these problems are going to be just like we did with our water calculations. It's going to be stoichiometry. So if I add acid, it's going to react with my conjugate base to make more of my original weak acid. If I add base, it's going to react with my weak acid to make more of its conjugate base. And so our general rules about our neutralization, what we did with that example is assuming these are going to completion, here's where you're using those guidelines. After that, we're going to be able to use our Henderson-Hasselbalch equation in order to do a new equilibrium calculation. And so this will allow us to do these without worrying about an ice table because my Henderson-Hasselbalch is essentially my simplified version of my equilibrium expression. So I showed you earlier the version of the Henderson-Hasselbalch that you'll see in your textbook. But remember that our A- and our HA initial concentrations, since they're in brackets here, they do need to be of molarity. But when we're talking about these solutions, my base and acid are always going to be located in the exact same amount of volume. So we could go ahead and simplify this version, and this would be the easiest one to use, where we're looking at moles of base over moles of acid because the volumes have canceled because they are the same. Let's look at an example with the same conditions as my water sample. So in this case, we don't have just water at the beginning, we have a solution. And so we have a solution of a weak acid and its conjugate base, meaning I can go ahead and use the Henderson-Hasselbalch equation. In order to use that, I'm going to need to convert my Ka into a pKa. Then I can go ahead and use the molarity of both my weak acid and conjugate base because they're in the same volume. I can go ahead and put them in my formula to give me a pH of 4.62. So let's compare this to how a buffer is going to be able to handle adding strong acid or strong base compared to just our water solution. We'll start with looking at the pH after I add 2 milliliters of HBr. In this case, we're still going to start off the same way. I'm going to look at how many moles of acid and base I have already in the buffer. So I'm doing this because all of my reaction of my acid is going to affect the concentrations or amounts of both my weak acid and its conjugate base. So I'll start by turning in my volume of my solution with the molarity from the previous part of the question to tell me how many moles of my acid I have. I can do the same thing with my moles of my conjugate base. And again, these are the amount of moles that are present in the solution at the beginning. We didn't need these numbers in the last example, but now that we're adding acid, we do. If I have moles of my weak acid and its conjugate base, I'm going to also need to know how many moles of HBr I'm adding. And so here I'm saying moles of acid added. This is just the moles of the HBr, not my weak acid that was already there. The key to these buffer questions is to remember that once I figured out my acid, how many moles I've added, I know that this is going to react with the base. And so if I think about my reaction here, I'm going to have my acid, which I've written in black, my conjugate base, which I've written in red. When those two react, I'm going to turn it into additional acid. So let's do this mathematically. I know how many moles of my conjugate base I have present. I know how many moles of acid I've added, which are going to react. That's going to decrease the amount of base that I have present in the buffer. At the same time, this is going to make more of my acid in purple. So while I started with 0.1 moles, the acid that I've added, the HBr, that's going to react with the conjugate base is going to create additional of my weak acid. And so I now have two new amounts of how much of my base is left and how much of my weak acid is left. Remember, all of the HBr is gone because it reacted with the base. Once I have my number of moles of acid and base, now that I know how many moles of base and acid are remaining, I can go ahead and use the Henderson-Hasselbalch equation. So at this point, I already have my value from the part 1, but I can also recalculate again if I need my pKa. I then can go ahead and use my Henderson-Hasselbalch, putting inside my pKa and my number of moles of base and acid to get my new pH. Now again, notice how little the pH has changed here relative to my initial pH of my buffer compared to how many units my water changed when I added the same amount of acid or base. I can always check these because I know that my pH should go down here because I added acid to the solution. Let's do the same thing looking at base. So if you want to try this on your own, you can pause the video. I'll have a practice question after this as well. So we'll still set this up the same way, where we'll have to figure out how many moles of both my weak acid and its conjugate base. These are the same values that we started with in the last question. So I'm not saying what is the pH after I've added 2 milliliters of acid and now 2 more milliliters of base. I'm saying at the starting point, if I added 2 milliliters of base versus 2 milliliters of acid. I'm going to set this one up the same way. So I have my concentrations of both my acid and base that are present in the buffer based off the concentrations given in the question. I then also now have how many moles of base I've added based off of my KOH. I can do the same thing here. This is going to be the reverse of the last question though, because since I've added base, this is the base that's going to react with the weak acid that's present. So I'm going to have the following reaction where my base being added in black is going to react with my purple weak acid, thereby creating more of its conjugate base. So I can start with how many moles of my acid I have. I'm going to lose some of my acid because it's reacting with its base. I then am also going to gain some of the conjugate base that I have made from the reaction to give me 2 new amounts of acid and base. From here, it's the same way. We're recalculating how many moles of each are present. Once I have my new amounts of moles for both my acid and base, I now can go right back to Henderson-Hasselbalch. I again will have my Ka handy from the previous parts of the question. I can then put in my pKa and figure out what my new pH is. And again, notice how little this has changed compared to my original pH of the buffer. I would expect my pH to go up because base was added, but this question really tries to show you how little pH is changing compared to how much pH was changing when we only had water present. This is a very similar example that you should be able to complete on your own. Let's pause the video now and try to complete. Okay, first things first, I can see that I have a weak acid. I can tell that it's weak because it has its Ka, and I know that it's not one of my 7 strongs that I have memorized. I also see that I have a concentration of its conjugate base, so I know that this is going to be a buffer. Once I've verified that it is a buffer, I can go ahead and use Henderson-Hasselbalch. I would first need to use my pKa equation to convert my Ka into pKa. I then have molarities, which I can use in my Henderson-Hasselbalch form because they're in the same volume. So I can go ahead and put in my pKa, put in my moles of base over moles of acid, and to get my original pH of the solution of 3.48. Now let's look and see how pH changed if I add base. So the first thing I'm going to still try to figure out is how many moles of my weak acid and its conjugate base are present. So if we're going to have my added base react with something, remember this is the part that needs to be done in moles. So I have my moles of weak acid in red, my moles of its conjugate base in purple, and I now have how many moles of hydroxide. This one is a little different from the last one because I'm getting 2 hydroxides for every 1 mole of barium hydroxide. So make sure stoichiometry keeps track of how many OH minuses you're getting per unit of your base. This gives me a number of moles of base. Again, this base is going to react with my weak acid. So I will use the amount of moles of my weak acid, and again I can write a reaction to help me figure out my base is going to react with the acid present, thereby giving me additional amounts of my conjugate base. I'll have my moles of acid, here's my moles of base that I've added, so that's going to go down. That means that my conjugate base is going to go up, and I now have 2 new amounts of my moles of acid and base. Once I have my moles of acid and base, I can go ahead and use Henderson-Hasselbalch again. So I already calculated my Ka, or my pKa from the last question. I can go ahead and put in my moles to get my new pH. I'd expect my pH to go up because I have added base to this question. Now, what if I add acid? I'm still going to have the same initial steps, right? So you can see that in both of these examples, you're still going to use stoichiometry to figure out how many moles of acid and how many moles of base are present. I also will need to figure out how many moles of acid I'm adding. Here is where we have an interesting problem, because if you look at what I've said, I know that this acid is going to react with the base, but look at what I have more of. I have more moles of acid from the HCl than I have present from my weak conjugate base. So while my acid's going to react with base, what's going to happen is I have too much extra acid, meaning I'm going to use my moles of acid and subtract my moles of base that are already there. This is going to give me 0.004125 moles of HCl, which, since it's a strong acid, tells me how many moles of H plus I have remaining. At this point, I have moles of a strong acid and a weak acid. And if this is the case, we know that we're going to have 100% dissociation of HCl, and we're only going to have a small dissociation of my weak acid. And so in order to calculate pH, I cannot add these two together, but the pH of my solution is basically going to be contributed only from my strong acid. So I have exceeded the buffer range here because I no longer have any more of its conjugate base, meaning I don't need to use Henderson-Hasselbalch. I will only need to convert to molarity. Notice the volume that I'm using here is the additive of my 75 milliliter solution I started with and the 1.5 milliliters of acid I've added. Now have my concentration of hydronium, which I can then use to turn into pH without having to use an ice table or Henderson-Hasselbalch. And here I expect this pH to be much lower because I've exceeded the buffer capacity and I now am only looking at an acid solution. The other way that's possible for making buffers is if I add a strong acid to a solution of a weak base, or if I add a strong base to a weak acid. Let's look at how this happens. So if I take a base and I add a strong acid to it, I'm going to then get a concentration of its conjugate acid. So I have my weak base, I have a conjugate acid, that's its conditions for a buffer. Same goes if I flip these, right? So if I have a weak acid and I add a strong base to it, yes, I'm going to make water, but I'm also going to make its conjugate base. So I can start with a weak acid, end up with its conjugate base. Both of these are our scenarios for when we could have a buffer. Here's an example of how that would work. Based on what we've done with the two examples on regular buffers, you should be able to handle this. Pause the video now and try it. Okay, so if we're looking at a solution that's involving a buffer, I can see that I have a weak base here and I'm adding a strong acid, meaning I can get its weak conjugate acid from as a result. I'm going to go and start to get everything into moles. I would start with my concentration or my volume and my concentration of my weak base. I now know how many moles of base I have. I can figure out how many moles of acid that I'm adding from my volume and molarity of HCl. That's giving me 0.0025 moles of HCl, which, since it's a strong acid, is going to give me just my H plus or H3O plus. I know that this acid is going to react with my base, so I can use the following reaction, that my acid in black is going to add to my base, giving me an amount of its conjugate acid. So I know that I'm going to start with my moles of base. My acid being added is going to reduce that amount to give me this many moles of base left. I then am going to have the same number of moles of its conjugate acid appear. So at the beginning, I only have a solution that contains 50 milliliters of 0.15 molar of my base. So I have no initial acid to begin with. I've created it by adding HCl. I now have concentrations of a weak base and its conjugate acid, so I now have entered the buffer region. Once I have my moles of base and acid, I can use my Kb and try to get to Henderson-Hasselbalch. Since Henderson-Hasselbalch uses pKa, I'm going to need to turn my Kb into a Ka. I cannot use Kb in Henderson-Hasselbalch. Once I have Ka, I can then turn that into its pKa, and then I can use the traditional form of Henderson-Hasselbalch, putting in my pKa, my log of both my base and acid to get my new pH. I have more base than acid, so I'd expect the pH of this solution to go up.